Hi guys, welcome back to our Radiation Heat Transfer Learning Journal. And of course, just to remind everyone while we are going through all of these messy formulas is that we want to find expressions for radiation heat transfer that are pretty representative of real life. And we went through black bodies because these are the ideal radiation heat transfer. They absorb and emit the most radiation and spectrum differences don't really matter. So yeah, the spectral effects don't really matter. So they're always our base case. So for now, let us do a very simple case. One simple example of heat transfer between black surfaces before we go on to more complicated. We upgrade the complication level to gray surfaces. Okay, so let's take a look at the heat transfer between black surfaces. So the first one will be, we'll just go through this example 5.1. Consider very long duct as shown in figure 5.2. Okay, that's figure 5.2. It is this one. This is a two-dimensional duct. This is EG 5.1 in Michael F. Modest textbook. Okay, so we'll have this case. Great. I think the snipping tool thing is there, but a little bit of faded look there. All right, but the thing is this: we have two surfaces of four surfaces, in fact, A1, A2, A3, and A4 in a very long duct, a very long square-shaped pipe in other words, but well, it's not a pipe, so we call it a duct. Okay, we have a duct, DUCT. One area T1. The opposite side is also at T1. One area which is A2 at T2 and the other at T4, 30 cm by 40 cm. Okay, all in all pretty simple. So the top and bottom walls are at temperature T1, 1000 Kelvin. The side walls are at T2, 6000 Kelvin. Determine the net radiative heat transfer rate per on each surface. So what is the net heat transfer rate from each surface? I'm just going to quickly go through and explain the solution that's presented in the textbook, so that at least we have some idea of what's going on. I'm not going to solve it on its own because there are going to be other more important things to cover, so I'll spend very little time on this. Okay, so alright, the solution says we may use either equation 5.7 or 5.8, but we shall use equation 5.8, which is the latter, since it takes advantage of the symmetry of the problem. Okay, i.e. it uses the fact that the net heat exchange between two surfaces at the same temperature must be 0. Okay, so what is this saying? Okay, I'll quickly go through because that's pretty straightforward. What it's saying is that the heat transfer between A4 and A2, it is 0 because the net, they're both black surfaces for one, and there's no driving force for heat transfer. They are the same temperature. Likewise, for the top and bottom, there is no heat transfer between these surfaces. So yeah, we can do that. So remember, I was talking about breaking the problem up into many smaller surfaces. Yeah. Okay, so Remember, this is the original integral we actually came up with. Okay, this is the original integral we came up with, but yeah. But the thing is that with integrals, we are splitting up the surface into many small surfaces. So what then is useful is to so-called break the surface up, as it was described, I think, in the last video. Yeah, you break the surface up, and then we work from there. That's how we get this summation sign instead of an integration sign. Okay, so that's how we get the summation sign instead of the integration sign. Okay, and how did this EBI minus EBJ come about? Okay, so this of course assumes, okay, the whole surface is enclosed. All right, the whole surface is enclosed, and normally if the whole surface is enclosed, all right, let me draw a picture. If the whole surface is enclosed, then let's say you have area I, and then you break it up into many small pieces here. Okay, so area I, this will be emitting heat in all directions, and all of them will be bound to hit on one other surface, right? So this surface 1, 2, 3, 4, and etc. So whatever is coming out from I is going to hit one of these surfaces at using and the amount received will be determined by the view factor Fij. That means from surface I to surface J, which is the 1, 2, 3 I was talking about here. Okay, so basically if we sum all the view factors from these surfaces, we will get back this okay, if we sum up the surfaces, yeah, EBI, right? EBI, we sum them all up with the view factors, we will get back this term. So we're just splitting this term, this emission term up into the radiation that's being received at each of these individual surfaces. So that's just what the summation is. So where did this term go? This term went into this EBI here, and actually if we sum everything up and multiply by the view factor, we will get back this term, because the summation of all the radiation received by these other surfaces is equal to the output radiation from this surface. Okay, so that's all that this summation sign is saying. Nothing too much to be concerned about. Okay, so these two basically, they mean the same physical thing, just a different way of mathematically representing them. And of course this one is better for segmented systems where we cut this enclosed black surface up into many small finite surfaces rather than an infinite number of small little surfaces as with the integrals. Okay, so anyway, this thing can be split up into 4 surfaces as we see here. And what do? They'll just begin substituting, right? In this equation, heat flux is expressed in terms of net radiative energy exchange between surface AI and AJ. Sure. Okay, so we use equation 5.7 and 5.8. Okay, so according to this equation, which is the 5.8, all right, we can take a look at Q1 first. Okay, take a look at Q1 first. Let's examine it term by term. So this is, we know the second term is incident radiation from the outside. But there's no incident radiation from the outside in this case. So this H not I is 0. Okay, so that's we can just ignore this and we just focus on the summation bit. Alright. And look at this. Okay, let's take a look at what this formula is saying. F1 to 2, we can consider the first term first, which is the radiation emitted from the first surface A1. So we look at EB1, EB1, and EB1. So what this equation is saying, EB1 into F1 to 2. So EB1 into F1 to 2, that is the radiative energy per unit area going from here to here. That's 1. F1 to 3 into EB1. This is surface 3. So this represents the term of radiation going from here to here. This is this term here. And then F1 to 4 into EB1 will be this. Now, of course, the self-view factor, we don't consider it because this flat surface doesn't quite see itself. Alright, so that's 3 of them. And then what else? We need to, there's no external radiation, so we need to consider the radiation coming from here to here. That is F1 to 4 into EB4. So there is a black body radiation being emitted from here to here. Okay. So F1 to 3 into EB3, that will be the radiation here from 3 to 1. And the EB2, which is from here, that's the emitted power from here to here. So the total emitted power from the surface 2 to surface 1 is this F1 to 2, the view factor from 1 to 2 into EB2. Okay, so that is the heat flux. The general expression, if we just copy and apply this formula. Remember, it's exactly the same meaning as this formula. It is just the outside radiation and the heat flux, the net heat flux leaving the surface. It's contributed to by the radiation leaving the surface, and we subtract off the contribution of radiation from other surfaces, which is this EBJ, and of course the radiation incipient on this surface from outside, which is this HOI. Okay, so again, HOI is 0, then we just have the net heat transfer between each of these surfaces, as kind of explained through this diagram here. Okay, so what we note, again, as we all said here, the heat transfer between A1 and A3 is basically 0. Why? Because EB1 equals to EB3, right? They're exactly the same temperature, so that becomes 0. So let's do Q1 equals F1 to 2. I'm just going to type it all out to make it clear. So this is the first term, which is the radiative heat transfer, net radiative heat transfer between these two surfaces. So 1 to 3, EB1 minus EB3 plus F1 to 4, EB1 minus EB4. Okay, so again, EB1 and EB3 are the same, so we can just eliminate that. And take a look. The symmetry of the problem dictates that the view factor between these two surfaces is the same as the view factor between these two surfaces. Alright? So basically, F1 to 2, the view factor from 1 to 2 equals to the view factor of 1 to 4. This is due to symmetry, as you can quite easily see on the schematics of this system. So at the end of the day, we'll have just 2 times of this. And since they are at the same temperature, EB4 equals to EB2. EB4 equals to EB2. Okay. Same temperature. And then basically I can just take this whole thing out. And that's Q1. Okay, that's Q1. And because the symmetry is the same, this Q1 is equals to Q3. Why is it the same? If you consider this surface and you see the symmetry of the problem, this problem is just a mirror reflection of here on here. Either way, you see the same, it's the same thing. So Q1 equals to Q3. Right? So yeah, we see the top and bottom are both at T1. We see the geometry is pretty much the same. It's a rectangle, 40 cm on top, 40 cm at the bottom, and 30 cm on both sides. And both sides are exactly the same area and same temperature, so you don't have to do extra calculation. Alright. So only view factors 1 to 2 and 2 to 1 are required. These are readily determined from the cross strings method. What is a cross strings method? You can check it out online. I'm not going to go through it. This is one of the very simple ways of determining view factors. Okay, they are over here. Cross strings method. Alright, so you basically have to measure the diagonals and the sides, and that will help you determine the view factor for very long ducts, for 2D surfaces, in fact. So that's the cross strings method, but I'm not going to go through that. Maybe I'll just see whether I can find something online. Cross strings method view factor. Hotel's cross strings method. Okay, I'll just put this in the link below, just in case you're interested in what the cross strings method is. I mean, yeah, though I'm not going to go through it. If you want me to go through it, yeah, you can leave a comment, and if I have time, I'll go through it, if I have time. Okay, so yeah, this is the cross strings method, and then we can do the same thing pretty much for Q2, right? Q2. Okay, if we want instead to determine what do you call that, heat transfer from this surface, we go through the same process. Okay, so Q2 equals Q4. I mean, if we're going to do all the same steps again, we're going to list all these things out, and then we find out, hey, the center, the heat transfer from here to here is 0. Then we're basically finding heat transfer from these two to these, the net heat transfer. Okay, and then we'll end up with this formula, very similar looking to this formula. So Q4 equals to 2 F2 to 1 bracket EB2 minus EB1. So we just find out the two view vectors, and then we can find out the net heat transfer. Okay, so basically we are applying this formula, and then we are just doing a simple view factor calculation here. And the cross strings method is as follows. You need to measure the sides and the diagonals. I'm not going to go through the method here, just showing you what's the physical application of whatever we have derived. And then we just over here they're just substituting real numbers. Okay, they're just substituting real numbers here. This is our calculation of view factor. And then here is where we substitute EB equals to n squared sigma T to the 4th Of course, if the medium is non-participating, n is basically just 1 because it's like a vacuum. Alright, so sigma t to the fourth, and then we'll just substitute those in, and then that's how we get the answer as I said here. But hopefully, the important thing is that from this very abstract concept looking thing, and you know this thing here is basically the view factor. Okay, what I'm highlighting here represents the view factor. So from a very complicated thing, we can actually look at something physical. We can do something physical and concrete and find out basically the heat transfer between each surface. And at least from a concept standpoint, it should make sense, because it's just the net heat coming in minus the net heat going out. And it's just that calculating each of these terms can be a little bit more complex, but once you find out what these are, I mean, heat transfer is just that between the black surfaces. The more complicated one is, of course, if we go to gray surfaces, which I think we are more or less ready to do in the next video. So thanks for watching this little example on heat transfer between black surfaces, and let's go through going through a problem can help us contextualize whatever derivations that are already there. Yep, and we'll go into the next video. Bye bye.